Welcome to the continued lecture for matrix force method. So far in the previous lectures, we have basically learned two main relationships. One is that the collective flexibility matrix relates the internal member displacements with the internal member forces. And then the other relationship is that the internal forces, they are related to the external forces by the force transformation matrix B. Now we continue further and we derive the relationship between the external force vector and the external displacement vector. In other words, this is the relationship that will be analogous to the relationship we have in the case of the stiffness approach. But here the vector u will come on the left hand side and the vector p will be on the right hand side. That is the main difference between the stiffness approach and the flexibility approach. Another difference is that here the p vector defines the state of the forces. So here we don't talk of the degrees of freedom. The matrix size is dictated by the size of vector P. Let us consider an arbitrary structure under the action of external loads P1, P2 and so on till Pn, and let the corresponding displacements be U1, U2 and so on till Un. So here we will utilize the principle of virtual work to derive the desired relationship. Let us assume that before the application of the forces P1, P2, etc., the structure was under the action of the virtual forces V1, V2, etc., and they were acting at the same points, that is corresponding to the vector P. And let's also assume that the magnitude of these components V is very small as compared to the P components. So now, based on what we have already derived, the internal forces resulting from the virtual external forces will be given by this relationship, that is the virtual internal forces equal to B times the V vector. So here for the internal forces we are using a subscript V to signify that they are from the virtual forces. So as we have learned in the case of the stiffness approach also, when we were deriving relationships for non-prismatic members, the virtual forces, they ride along the actual forces and thus they perform a virtual work, and the virtual work is equal to the product of the virtual force multiplied by the actual distance. So the factor of half does not come here. So now when we use the principle of virtual work, all we have to do is we have to equate the external virtual work with the internal virtual work. Just like the external virtual forces V1, V2, V3 and so on, they are performing the external virtual work. Similarly, the internal forces which occur because of the applied virtual forces, they also perform internal virtual work. So the two are equal. So the external virtual work is given by the sum of product of all the external virtual force components and the corresponding real displacements. Similarly, the internal virtual work is given by the sum of product of the internal forces generated by the virtual external forces and the corresponding actual internal displacements. So here, by making use of the force transformation matrix B, the internal virtual forces can be expressed in terms of the external virtual forces by using B into V. So with this substitution, we proceed further. By this substitution and by algebraic manipulation, we can find that we derive a very simple relationship between the external displacement vector u and the internal displacement vector d, and they are both related by B transpose. So we can say that u is equal to B transpose d. So we must note that on the other side, d is equal to B into u. So when we change the positions of u and d, what happens is that B is replaced by B transpose. Now d can be further expanded in terms of the collective flexibility matrix and the vector of the internal forces. So we get a relationship like this between the external displacement vector u and the internal forces F. Now we must note that the internal forces, they are further related to the external forces P by the force transformation matrix B. So let's do this substitution also. By this substitution, we get following relationship, that is the vector u is given by B transpose into Fc into B and multiplied by the P vector. So now we have a relationship connecting the external displacement vector u with the external force vector P, and this is basically connected by B transpose Fc P. Hence, by definition, this term B transpose FCB must be the total structural flexibility matrix. So this is analogous to the total structural stiffness matrix we had derived in the case of the direct stiffness approach. So we now have our final expression for FTS. Before we solve some example, let us summarize the procedure for analysis of statically determinate structures by using the matrix force method. The first step is that we need to specify the prescribed forces or the force vector P. Now the directions of the positive external displacements, they are governed by the P vector, and P vector also dictates the size of the total flexibility matrix of the structure. So FTS will have a size n by n, where n is the dimension of the vector P. After this, we define all the internal forces, we identify them, then we form the flexibility matrix of each member and then arrange them in the form of the collective flexibility matrix. Then the next step is to form the force transformation matrix B, which we have learnt that we have to apply a unit force one by one along each of the external forces and find out what are the internal forces induced in various members. So that will give us the matrix B column by column. So after this step, the next step is that using the matrix B, we can find all the internal forces because they are given by B times P. Then we form the total structural flexibility matrix by the product B transpose Fc into P. Once we have the FTS, we can immediately use that to obtain the external displacement vector U, which is equal to FTS into P. Having learned this procedure, let us continue with example 1. So we have already formed the B matrix and the collective flexibility matrix. So now, by making use of what we have learned, we can find out the total structural flexibility matrix B transpose times FC into B. So we have these matrices available. So once we substitute, we get the final FTS, that is 2 by 2, and this is basically L by EA is common, and inside we have 1, 0, 0 and 1 plus 2 root 2. So this is the FTS. So now we can use it to obtain the external displacements along P1 and P2, that is the displacements U1 and U2, which are shown. So this will be equal to FTS multiplied by P1, P2. So we have the answer. Similarly, we can find out all the internal forces by just the product of B and P. So this step you can do yourself. Let us implement this in example 2 also, that involved a cantilever beam. So here we have the B matrix, which is 4 by 2 and FC was 4 by 4. So once we perform B transpose times FC into B, our result will come out to be 2 by 2, which is consistent with the fact that there are only two prescribed forces P1 and P2. So in this particular case, we will obtain the displacements below P1 and P2. Let us go a step further in this example. Suppose we had also desired the end rotation, which let's say we denote by symbol U3. Then what would have been the case? How would we solve it? Now this is force method. Here the governing quantities are the forces. So if we want a rotation at the free end of the cantilever, then only way is that we have to apply a fictitious moment, say P3, and derive the corresponding matrices like FC and B for the extended force vector. Now after final solution, we have to input the value of P3 equal to 0. Then only we will be able to get the displacement U3. Now the reason here is that the forces are the main unknowns. Unless we specify the forces, we will not be able to find the displacements at the desired locations and in the desired directions. So displacements can be either translations or rotations. Hope this concept is understood well. So if you have understood the procedure for determinate structures, it's fairly simple now to extend the matrix pose method to indeterminate structures. The method is that in the case of an indeterminate structure, we have to first convert it into a primary structure by choosing appropriate redundant forces. The choice should be such that we are obtaining a stable structure. So we can view our original structure to be a superposition of the primary structure acted on by the applied forces and also by the redundants. The first step is to express the internal forces by utilizing the B matrix. So here, in terms of the coefficients of the B matrix, we can express the internal forces as the linear combination of the applied loads P1, P2, P3, etc., and After this, the further linear combination of the redundants x1, x2 and so on. So now we have a modified B matrix at our disposal. That is, when we express the internal forces in terms of the product of the B matrix and the external forces, we have two components of the B matrix, one for the prescribed forces P and other for the unknown redundants X. So similarly, we have the addition in the case of the displacement vector also. So the displacement vector also now consists of two parts, one the unknown displacements UP and the prescribed displacements UX, which are known. They are either 0 or they have fixed value. So in essence, we now have the internal forces given by a modified expression where we are doing a partitioning of the B matrix. And in addition to the P vector, we are also adding the X vector, just like in the case of the stiffness approach also we had the X vector. So here the X vector will come just below the P vector. In order to solve the resulting system of equations, we have to make use of compatibility conditions. That is, at the points of the redundants, the displacements due to prescribed forces P and the displacements due to the redundants X, their sum must be equal to the prescribed displacements at those points. That is, in the case of structure on rigid supports, the sum would be equal to 0. If the structure is on settleable supports and we have knowledge of the support settlement, then the combination will be equal to the prescribed value of the displacements. Here the expression for the displacements will remain essentially same. Only thing will be that we shall have the modified matrices for B. In addition, we'll have the redundant vector joint below the force vector. So we can now substitute the expanded B matrix into the formulations, and then we get this kind of expression. So here the BB transpose and BX transpose, they are now pre-multiplying the second part, which is composed of FCBP and FCBX. Please note that the number of rows of BP and BX, they are same. That's why FC can easily multiply it. So now once we finish multiplying this two matrices, one here appearing as a vector and the other appearing as a row, then we get something like this. So on the left side we have the vector of the displacements consisting of the unknown displacements UP on the top and the prescribed displacements on the bottom. And on the extreme right hand side we have the prescribed force vector P, and below it we have the vector of the redundants. And these two vectors, that is the displacement vector and the force vector, they are now connected by an expanded form of FTS, because once we do the multiplication as shown in the previous slide, we get four components of now FTS, and these components are FPP, FPX, FXP and FXX. These are given by FPP is given by BP transpose into FC into BP. FPX is given by BP transpose FC into BX, and FXX is given by BX transpose FC BX. Now Fpx and Fxp, they are basically transpose of each other. So this process gives us the system of equations necessary to obtain our results. So we can start with the second set of system of equations, that is involving ux, because these are the prescribed displacements. If they are 0, then our job is very simplified, and x is simply given by the expression minus fxx inverse into fxp into p. If ux are not equal to 0 but they have a fixed value, then all we have to do is just again write the second equation and derive it with the condition that ux is not equal to 0. So that is a homework for us. So in any of the two situations, whether ux are 0 or not, we can obtain now the reactions or the redundants x. Once we have the redundant x with us, we can obtain the internal forces by making use of the force transformation matrix, because we have already derived it, and now we have the components bp and bx, and since x are known, the internal forces can be obtained now. Finally, the unknown displacements, they can be obtained by making use of the first set of equations, that is up is equal to fpp into p and fpx into x. Once we have x now, so we can easily obtain the unknown displacements also. So this is the total procedure for the indeterminate structures. It's just an extension of the procedure for the determinate structures. And now we have these components fpp, fpx, fxp and fxx. So they are analogous to the various components of the total structural stiffness matrix. And in the case of the direct stiffness approach also, we usually begin with the second equation and then we go to the first one and obtain the displacements. So here also the procedure is more or less analogous. Hence the procedure can be summarized as follows. Number 1, we have to identify redundants. This can be done once we obtain the degree of static indeterminacy, and we have to choose the redundants such that we are obtaining a stable structure. Number 2, we now define the vector of the prescribed forces and the redundants. Then after this, we have now the main steps 1, 2, 3, 4, 5 and 6. So the first is that we define the vector of the internal forces, and then we form FC, that is the collective flexibility matrix. Then we form the matrix B. Now this matrix B will have two components, one for the prescribed forces P and the other for the unknown redundants X, so BP and BX. Once we have the B matrix, in total we can obtain the various components of the total structural flexibility matrix, namely FPP, FPX, FXP and FXX. Now after the total structural flexibility matrix has been formed, we can start solving the equations, beginning with the bottom as already explained. So if ux is 0, we get direct answer. If ux is having a prescribed value, then also we can get the answer for x. So once we have x, we can then obtain the vector of the internal forces as well as the unknown displacements of the structure.